Alrighty, here we are, back at it again with Vectors Part 2. And here we're going to go a little bit more into some of the physics, but I've got some more notation to go over, then a little bit more math, and finally how this all wraps up together. I'm going to go over something called like bracket notation, and that will make sense when we get into it. Sounds like a funny name right now, but you'll see. Then we'll go over like integrals as dot products. And yes, we can take integral as a dot product, and I will show you more on that later. And finally, just spin vectors, because I thought I'd put them in there as we can represent quantum spin as vectors. Anyway, here we go. So, first up, bracket notation. But first, we better go over some notation. So remember, we have like vectors. We'll call this vector v. Let's say this is equal to 1, 2. And we have a vector transposed is equal to this 1, 2. And a vector transpose times a vector is just going to equal some number, which is like what we called the dot product. A number or dot product. Now, in quantum mechanics, this notation is not very good because it gets kind of ugly. And also, it's not only transpose vectors that we worry about, it's also complex conjugate vectors, because as you might recall, earlier when we were doing integrals, we had something like this, where we had psi star times psi. And I mentioned that imaginary numbers are really important. Well, they come back here again as well, because we can have a transpose complex conjugate vector. I gotta erase some of this. Like if, let's say that u vector is equal to I and let's say 4. Well, then we have to take u transpose and a star in order to do our stuff, which would be like negative I 4, and this doesn't look good. So instead we're going to do something called like bracket notation. And we're going to rewrite it like this. So let's say we'll stick with a vector v. This is equal to this notation. As you can see, we swap out this arrow bit for this little funky looking thing. And that's because we can take, this is still equal to the same thing, of course, 1, 2. But this enables us to take the dot product. Instead of writing v transpose star or something, we can instead write it like this, v. This is called the bra. And this is the ket. And in order to take dot product of v transpose star times v, but we just do this. We have the bra vector and the ket vector. Ta-da! It's a bra ket. That's why it has this funny name. And from now on, I'm going to be trying to use some of this notation just because it's more elegant. Just know that this is essentially the same as v complex conjugate times v. Now, let's suppose that we are dealing with something that is discrete. For example, we have like an atom with very discrete energy levels. And if we want to describe some of these energy levels, we obviously can't use a wave function because they're discrete. So we actually have to use a vector. Let me get a better representation. Like you can imagine this is like the atom. Let's say that this is equal to 1, and let's say that this is equal to 2 of let's say psi, we can actually represent this like this. So the vector psi is equal to the column vector of 1 and 2. And that's very simple. And let's say that we want to find, I don't know, the because this can represent any discrete system like that, but it can also do something a little bit cooler, which is where we're going to get into the integrals. Because let's say that we have a function like this. You might have heard something where, and you want to take the integral of this vector. Sorry, that you want to take the integral of this. You might have heard that we can do something like create boxes underneath and approximate it. And we're going to do something a little bit like that here. But instead, we're going to call it a vector. So we'll call this x1, and this one x2, and this one x3. And this wave function is called psi. Well, we can actually, like you can see this bit is up here, this bit is here, and this bit is here. We can actually approximate this vector, this whole wave. We can approximate it using what we call it psi1 and psi2 and psi3. It's an approximation, of course, because in order to get a real wave, we'd have to have like infinite number of vector components. But we're just going to approximate it because that can make this easier, And how do we find, say, the probability? You might recall we had something like, where we take the integral, and we take psi star, and another psi. And that's great if this psi bit is nice and easy, but what if it's like all over the place, like spaghetti or something, and we don't want to do that? Well, we can actually approximate it by just turning psi into a vector, just like here, and then we can just take the dot product with itself. So we'll take the bra of psi and the ket of psi, and this should be approximately equal to the probability of the particle, in between, say, this bit and this bit. And, this gives us a pretty simplified way to solve very complicated integrals. Because trust me, sometimes these integrals are nasty, and you don't want to work them out. And so you can approximate them like this. And you can also use this, for example, for say the waves. Like if you have an x wave function that looks something crazy, and a momentum wave that looks something slightly crazy, you can also just take the dot product. You can turn this into an x vector and this into a p vector. And there are some other steps I'm skipping over, but you can basically do the products, which we won't get into. Essentially, if you have like a vector and you take the vector inner product, the dot product, then it can be used in approximation of the probability. And we'll see more uses of vectors another time. This is just like a simple use, so you can see what all that dot product stuff was for last time. Now you might wonder, well, why are we learning about linear independence and stuff? And the answer is spin. So I might recall from a while ago was vector particle spin. We can have like a particle launcher, and we can have, some magnets, and call this north and south. And, some of the particles will wind up going up, and some of the particles will wind up going down, and that never end up anywhere in between. Well, we can also represent these as vectors. For example, this one we can represent with a vector 0, 1. Or we can represent, that's a bad color. Or we can represent this as this. And you might be asking, well, hang on, why isn't the downward vector just a -1? And the answer is linear independence. Linear dependence. I'm out of room. But essentially, like if we treated, say, the upward vector like this, and the downward vector like this, then this would just mean that they're kind of like part of each other. And we'll see more about this when we get into like matrices. But this would basically mean that up is equal to down, which won't help. And in order to make all the math work out, we actually treat it a bit more like this. This way, this can go in this direction however it wants, or this direction, without adding to the upward vector. You can think of, for example, if we were to say rotate this some direction, this might gain like a negative sign because it's pointing the other direction. And this might gain a negative sign, but it's still going to be different. Like it's still going to be in the up and down sort of realm. It's just pointed a different direction because we flipped the apparatus upside down. But anyway, these vectors are linearly independent. And you might have heard of something called a quantum computer. Oh, hang on, I cannot spell. Quantum computer. And in quantum computers, this is exactly what happens. Uh, like in normal computers, you might have like a 1 and a 0. Well, in quantum computers, these are represented exactly like this. So you have the 1 vector, which is just 0, 1. And you can have the downward the 0 vector. It's not really a 0. Let's just call it a 0 because of how computers work. Because you can only have 0 or 1. And, this is just the 1, 0 vector. Anyway, it's not much else to this because we haven't included things like matrices yet. I guess this is probably a short video because there's not much to go into without the matrices, which we'll go over next time. But maybe just consider this like a teaser or a taste test for how some of the vectors work sometimes with quantum mechanics. All you need to know is that we can represent quantum states as vectors instead of equations. And some mathematicians might not like me to say that, but I'm going to say it. And sometimes, you can use these vectors to approximate nasty looking integrals, like instead of doing something, like let's say your equation of psi is equal to like, I don't know, 1 minus sine plus 4x. And then you have to like take the integral of essentially like psi squared because there's no imaginary components. That's going to be like a nasty, horrible integral for x. Yeah, this whole thing squared, and that's going to be a lot of work. And it might not even be solvable. Sometimes, it might be like an impossible integral that no one can solve. But instead of doing that, what if we find out that like psi 1 is equal to like, let's say 4, and psi 2 is equal to like 7, and psi 3 is equal to 1. But then we can just make it so that psi is equal to 4, 7, 1. And instead of doing some nasty integral, we can just do like 4 squared plus 7 squared plus 1 squared. And it'll be sort of close to the probability. And so instead of breaking our butts doing some impossible integrals, we can just simplify it using this, vector notation. This is vector product. And we'll go more into this stuff with like matrices and how matrices can modify vectors. But anyway, that's all for now. It's not that much. And next time we'll go into intro to matrices. And see you next time.